Yay!
Okay, one example that we'll do in rotational problems is to use the concept of energy conservation. So one cool thing that we can solve this way is looking at old-fashioned like a catapult or a trebuchet. And so the idea is that I have some little mass, something over here, and what I want to do is I want to fling this thing so that it kind of leaves going that direction. And how I do it is I load a big mass on the other end and let it swing down. There's a pivot point right here. And so the big mass swings down, and then it just sort of flings the mass, the little mass, off the top. So what I want to know is, let's set it up where little m is little l away from the pivot point, and big M is big L away from the pivot point. Usually, you want the pivot point to be as close to the big mass as possible for reasons that we'll see in just a minute. So if we set all that up, how fast, given all these masses and lengths, how fast is that thing going to be flung off there at the top? So, okay, what we're going to do is use conservation of energy. And you know by now, what that means is energy initial is energy final. What is the initial energy? Okay, let's say part of it is choosing our coordinate system. Let's say that this initial position right here is going to be where the potential energy, the mgy, right, is going to be 0. Okay, so initially nothing is moving, and I've just loaded the big mass onto the platform. So the initial energy is going to be kinetic plus potential. The final energy is going to be, again, kinetic plus potential. Nothing is moving initially, so I don't have to worry about that. And just by construction, just because we're defining it this way, the initial potential energy of both masses is going to be 0. They're both at the same horizontal level. So that's going to be 0. No problem. Okay, so this means that 0 is going to be equal to the final kinetic energy. All right. Now there's two objects here, right? And they're both pivoting around. They're both revolving around this pivot point. So each of them has a kinetic energy of rotation of 1/2 I omega squared. Okay, so this is going to be 1/2 times I omega squared. In fact, let me write it like this, because it's going to be different for each mass. Right? So this is going to be the I for, let's write it, the little mass, omega squared plus 1/2 I for the big mass, omega squared. Okay, and now the potential terms. Okay, in the final position there, the big mass has gone down a distance big L. So this is going to be minus mgl. And the little mass is now up at a height little l. So this is going to be plus mgl. There we go. Those are all of our energy terms. So all we have to do now is just solve for omega. And then we'll solve for v. We'll get a linear speed of this thing at the end. So omega squared is equal to, we'll take the square root later. It's going to be equal to mg big L minus mg little l on the other side. And then actually, you know what? Let's get that 2 out of here. So this is going to be a 2 minus 2 mg little l. It's because we got a half in front of the other terms. And then I'm going to divide by I little m plus I big M. All right. Let's see, I can factor out a 2g. And then on the bottom, what is I? What is the moment of inertia of the little mass? Well, it's just m little l squared. So it's just going to be ml squared plus, and for the big one, it's m big L squared. Well, there we go. So all I have to do now, and this is easy because I can just do it like this. I can just take the square root. There we go. Let's put some numbers in just to see how practically this might work out. Let's see. Suppose it's a big, so that's M is a big rock. So big M is 100 kilograms. You can verify all this yourself. Little m, suppose it's like a baseball. What's the mass of a baseball? It's like 150 grams. So it's 0.15 kilograms. Let's say big L, we're nestled in close to the big rock. So it's 0.5 meters, 50 centimeters. And little L, suppose the whole thing is like 5 meters. So this would make this 4.5 meters away. So it's just it's a long launching rod. I think that's all we need, right? So if you plug in all of these numbers, what you should find is that this turns out to be about 6 radians per second was the units for omega. But then if you want the linear speed, so how fast is the baseball going when it's released up at the top? Well, remember the connection between linear speed and angular speed. It's r omega. So it's just going to be 4.5 times that. So it's going to be something like, what would that be? Like 27, I don't know, pretty close. 27 meters per second, something like that. So if you fiddle with these things, you can get your trebuchet to launch something with a faster speed. How do you do it? Make m bigger, right? Make big L shorter. Make the rod longer. Make big L longer, and so on. So you can kind of tune these and get your trebuchet to launch with the speed that you want.